Strong and weak acids and bases, Part 1. The nature of weak acids and bases, Ka and Kb. The equilibrium law applies to acids and bases. A weak acid, definition, is one which does not dissociate completely in water. A weak base is one which does not dissociate completely in water. For any weak acid, acids being hydrogen ion donors, the acid Ha will dissociate to form H+, but dissociation is not complete. In fact, it's very slight. I can write an acid dissociation constant in the same way that I would write an expression for an equilibrium constant. Here, my equilibrium constant K now becomes Ka, specific. The greater the value of Ka, the more the equilibrium lies towards the products. The more the acid has dissociated and the stronger the acid is. I could say the same thing about a base. Example. In the case of ethanoic acid, the ionization equation, the reaction with water, and the Ka expression become. I see my acid combining with water. Of course, we know H3O+ is the ion produced, but I can summarize that with the equation below and write my Ka expression for that weak acid. For a weak base, bases being hydrogen ion acceptors, I can write an expression for Kb in just the same way that I would write an equilibrium expression for any reversible reaction. My example, ionization of ammonia. And from there, I can write my base dissociation constant Kb for the weak base. Two very useful assumptions that can be made. Hydrogen ions or hydroxide ions from the ionization of water is ignored. Water dissociates slightly to give H+ and OH-, but the concentrations of either are generally around the region of 10 to the power of -7. Very small, ignored. For an acid, concentration of hydrogen ions equals concentration of the anion it makes on dissociation. Let me go back for a moment. For an acid, we see that Ha is produced at the same time as A-, concentrations taken to be the same. For a base, here we are, OH- ions produced are taken to be the same as the concentration of BH+. They're made at the same time. Also, concentration of an undissociated acid or base at the start is taken to be the same as its concentration at equilibrium because dissociation is very slight. Some practical procedures to distinguish between strong and weak acids. These are simple procedures to determine the relative acidities or basicity of substances. It's important that in all these tests, acids or alkalis which are being compared are at the same concentration. All the measurements taken in the procedures below, there are 3, are dependent on the amount of hydrogen ions present in the solution. For example, when comparing 2 1 mole per cubic decimeter solutions of H2SO4 and HCl, there are twice as many hydrogen ions in H2SO4 as in HCl. So, for example, H2SO4 conducts better. I can compare the pH of substances. Compare the pH. If the pH is higher, the acid is weaker. You may have realized already that questions asked on this are almost always focused on acids. Compare the conductivity of the same concentrations. Measure the conductivity of solutions of the same concentration. The acidic or basic solutions with the largest concentration of ions will have the highest conductivity, as those with the highest conductivity have dissociated more. And if one substance has a higher conductivity than another, it's produced more ions. It's dissociated more, it's stronger. I can compare rates of reactions with reactive metals. This is for acids. E.g., measure the gas production. Metal plus acid gives salt plus hydrogen. Strong acids react at higher rates than weaker acids. If I'm generalizing, and I think this is one of the most useful rules, if an acid contains carbon, it's a weak acid. If a base contains nitrogen, it's a weak base. I need to know that the substance is acidic to begin with to say if there's carbon there, it's a weak acid. I need to know that a substance is basic in the beginning in order to say if it contains nitrogen, it's a weak base. I look at my strong acids. Typical acids we use in the lab: HCl, H2SO4, HNO3. HI is also a strong acid. My weak acids: carbon, carbon everywhere. Organic acids are weak. Strong bases: the hydroxides and oxides of group 1 and 2. Weak bases: I see nitrogen everywhere. The rule highlighted in yellow is such a good one to know. Now, for a conjugate acid-base pair, Ka multiplied by Kb is Kw. Looking at an acid, Ha, and its conjugate base, A-, the acid will dissolve in water to give hydrogen ions and the conjugate base. I can write my Ka expression. In the reverse reaction, A- reconverts Ha. I can write my Kb expression. If I multiply those two expressions together, if I multiply Ka times Kb, we'll see some things cancel, and I'm left with Ka multiplied by Kb is the concentration of hydrogen ions multiplied by the concentration of hydroxide ions, which is Kw. Some questions based on past paper questions I've seen over the years to end with. At the end of each question, I'll pause for a moment, give you time to think, and then I'll show the answer. So, which solution? Okay, 1 mole per cubic decimeter, that's just to say they're all of the same concentration. Which solution would have the highest conductivity? Now, my answer is D. Conductivity is higher if there are more ions in solution. I've got a weak base, that's A, and a weak acid, that's C. Few ions, only partially ionized. HCl and H2SO4 are strong acids, but H2SO4 gives more ions when dissolving, as you can see in the equations. Which of the following dissolve to form weak acids? And my answer, C. I can see carbon in option 2 and option 3. Anything based on carbon is a weak acid. HCl is a strong acid. My only 2 and 3, that's C. What's the correct order when the following solutions are placed in order with the lowest pH placed first? And what's the likely pH of a 0.1 mole per cubic decimeter solution of ethylamine? Formula given. Okay, so my answer is B. H2SO4 is a strong acid, pH, around about 1. Based on carbon, ethanoic acid, CH3COOH, is a weak organic acid, pH around 4. NH3, based on nitrogen, a weak base, pH around 10. And NaOH, my strong base, pH around 14. B. What's the likely pH of a solution of ethylamine? Well, it's based on nitrogen. It's a weak base. It's not going to be over 10, but it is going to be over 7. Answer C. Ethylamine is an organic molecule containing nitrogen and so is a weak base. Nitrous acid is a weak acid and nitric acid is a strong acid. Distinguish the terms strong acid and weak acid and give equations for the dissociation of each acid. And then magnesium powder is added to solutions of the two acids with the same concentration and at the same temperature. Give 2 observations that would help you to identify the nitric acid. For the first part, strong acid completely dissociates, weak acid partially dissociates. Semicolon showing that's 1 marking point. My equations. Nitric acid breaks up completely. Nitrous acid only breaks up slightly. 3 marks. And when my magnesium powder is added, the strong acid, the nitric acid, will give you faster effervescence, faster bubbling. It's going to give off more heat, it's going to get warmer. And the reaction will be faster. The magnesium will dissolve faster or the reaction ends faster. Any 2 from 3. That's it. If you found that useful, please hit like. Please subscribe to be informed of more content.